Hello and welcome back, and if you are new here, welcome, we are very glad to have you here. In today's video we will start with basic definition of transistors. We will present a brief history of their development and what transistors are used for. Before we begin, we would like to take this opportunity to say thank you to you who have subscribed to our channel. Special thanks go to all of you who have left comments and inquired about our videos, or just posted interesting questions of your own. Your kindness in communication and the time you have chosen to spend watching our videos is greatly appreciated. We would do a great disservice to our viewers if we're to skip a brief overview of transistor development and fascinating story that accompanied the development of this ground-breaking milestone component in modern technological development. You watching this video on YouTube would not be possible if there were no transistors in existence. So, it is only fair to present short and honorable homage to Its Majesty, the transistor. Before transistors, vacuum tubes were used for electronic amplification and switching. These were bulky, power-hungry, and unreliable. Early research into semiconductor properties laid the groundwork. The concept of a field effect transistor was proposed by Edgar Lilienfeld in 1925. However, his work was not widely recognized at the time. The first working transistor, known as the point contact transistor, was successfully demonstrated on December 23, 1947, at Bell Laboratories by John Bardeen, Walter Brattain, and William Shockley. In 1948, William Shockley introduced the bipolar junction transistor, which entered production in the early 1950s and led to the first widespread use of transistors. This type of transistor used a sandwich of semiconductor materials. Gordon Teal at Texas Instruments created the first silicon transistor. Silicon proved superior to germanium due to its stability at higher temperatures. The metal oxide semiconductor field effect transistor, MOSFET, was invented at Bell Labs between 1955 and 1960. This breakthrough led to the mass production of MOS transistors, which became the basis of processors and solid-state memories. Transistors have since become the backbone of nearly all electronic devices, from radios to computers, revolutionizing the way we use and interact with technology. The development of ICs, or chips, allowed for the miniaturization of electronic devices. Moore's law predicted the exponential growth in the number of transistors on a chip. Ongoing research focuses on nanotechnology, new materials, and advanced designs to further improve transistor performance, with modern chips now contain billions of transistors. Transistors replaced bulky vacuum tubes, leading to smaller, more efficient electronic devices. They enabled the development of computers, radios, televisions, and countless other technologies. Transistors are the foundation of the digital age, driving innovation in computing, communications, and artificial intelligence. The transistor's history is a story of scientific discovery, engineering innovation, and transformative impact on society. In this video, and moving forward, we will deal with two basic types of BJT transistors, the NPN and PNP transistors. The BJT stands for bipolar junction transistor. A BJT is a solid-state device, in which the current flow between two terminals, the collector and the emitter, and is controlled by the amount of current that flows through a third terminal, the base. The three terminals, the base, B, the collector, C, and the emitter, E, represent junction points, or simply put connection points, between transistor and the rest of the circuit. Unlike resistors, capacitors, or diodes, which all have two terminals, or two connecting points, transistors have three. Also, the way you connect these three terminals to the rest of the circuit, plays an important role in how the transistor operates. The way you can tell the difference between NPN and PNP transistor is by looking at the orientation of the arrow at emitter terminal for both types of transistor. In NPN transistor, the arrow points out of emitter terminal, and for PNP transistor points into emitter terminal. If you have paid enough attention, and figured it out by your own, the direction of current from the collector to the emitter is the same for both types of transistors. Regardless of the type of transistor, the current is sourced from power source and starts flowing from collector through transistor, and exits through the emitter, as the red arrow points. The animation makes it more clear and easier to understand. From previous video we have learned that there is a general consensus in the industry, that markings of direction of current through the circuit will be, what is called an engineering direction of current, from positive to negative terminal of power source. As a consequence of that consensus, now the holes are the facilitators of electromagnetic field propagation through electrical circuits. If you have not seen that video, please watch it, there you will find very detailed explanation of this topic. As you can see, for both NPN and PNP transistor, the current springs from positive terminal of the battery, enters the collector, or if you prefer, the collector collects the current, then the current passes through the transistor, and exits through emitter terminal, and sinks back to negative terminal of the battery. Another way of saying this is, that emitter emitted current back to the negative terminal, hence the names, collector, this terminal collects the current into transistor, and the emitter, this terminal emits the current from the transistor. And as you can see, the direction of current for both NPN and PNP transistor is the same, so what is the catch with the arrows? Are they drunk? Well, whoever decided to design and draw symbols for NPN and PNP transistors like this, with arrows pointing out from emitter for NPN, an arrow pointing in the emitter terminal for PNP transistor, deserves a VIP place in hell, and if there is no hell, there should be one, especially for this individual. This ambiguity with these arrows is source of great confusion for beginners who are trying to learn about transistors. If you pay closer attention to the graphics on the screen, the red arrows, ones that marks the direction of base current, or more precisely to say, the current flowing into the base terminal of the transistors, are aligned or concordant with the orientation of the markings on the transistor symbols. For NPN transistor, the base current flows into base terminal, and for PNP transistor, the base current flows out of the base terminal. From graphics, we can see that collector and emitter current are sourced from battery, or any other source of DC power, but from where does a base current come from? That is very important question, since the base current is the most important aspect of transistor operation. The base current determines the mode of operation of the transistor, but we will leave that aside for now, and focus just on the direction of current flow for NPN and PNP transistor, respectively. Although, the most common case is that all of the three terminals, the collector, the emitter and the base, all share the same power source. For this case alone, we will draw a circuit where base terminal will have a source of power on its own. So, for NPN transistor, we will connect the battery, so that the base of the NPN transistor is connected to the positive terminal of the battery, and negative terminal is shared with the emitter terminal. Analogous to NPN, for PNP transistor we will do the opposite. We will connect the base terminal of the PNP transistor to the negative terminal of the battery, and positive terminal will be shared with the collector terminal. Now, some of you, who are more experienced in transistors will notice that there is a bunch of resistors missing, but this is not by omission. We want animation as simple as possible, and we just want to demonstrate various directions that base current takes in two types of the transistors. Now, for NPN transistor, the current springs from positive terminal of the battery, enters the transistor through the base terminal, and mixes with current flowing from the collector terminal, and together, through the emitter terminal, they sink into negative terminal of their respective batteries. So, for NPN transistor, we can say that the function of the emitter terminal is to add together currents from the collector and base terminal, and sinks them into negative terminal of the power source. Hence the famous NP transistor formula for the emitter current, the emitter current is equal to the sum of the collector and the base current. Analogous for PNP transistor, for PNP transistor, the current that is sourced from positive terminal of the battery, through the collector terminal enters into the transistor, and there it splits into two currents, the base terminal current, which exits the transistor and sinks back into negative terminal of the battery, and the emitter terminal current, which then exits the transistor and also sinks back into negative terminal of the battery. So, for PNP transistor, we can say that the function of the collector terminal is to split current into two separate flows, one that will exit the transistor through the base terminal, and the rest of the current, that will exit the transistor through the emitter terminal. Hence, the famous PNP transistor formula for the emitter current is equal to the difference between the collector and the base current. For NPN transistor, the collect and base current have the same direction so they add up, but for PNP transistor the collector and base current splits into two different directions, so the remaining emitter current is what is left over, when you subtract the base current from the collector current. For both types of transistors, the collector, the emitter and the base currents are three most important parameters for doing calculus. It is of utmost importance that you fully understand and comprehend directions in which each of the three separate currents flow through the transistor, and their directions, respectively. In summary, for NPN transistor, the base current goes into base terminal, adds together with the collector current, and exits the transistor through the emitter terminal. For PNP transistor, the collector current splits into two parts. First part exits the transistor through the base terminal, and second part exits the transistor through emitter terminal. The direction of base current is the single most important factor separating NPN from PNP transistors. Simply put, the base current adds with collector current for NPN transistors, and for PNP transistor, the base current is subtracted from the collector current. For both transistors, what remains is the emitter current. Both NPN and PNP transistors work in one out of two modes, either as a switch or as an amplifier. The mode of operation is determined by the amount of current present at the base terminal of the transistor. If base current is equal to 0, or less than some predetermined value A, then transistor is in so-called cutoff mode. In this mode, the transistor is analogous to an open switch in the circuit. No current flows between collector and the emitter. If the base current is greater than value A, and smaller than value B, then we say that transistor is in active mode, and acts as an amplifier. In this mode, the emitter current is proportional to the base current. If base current is greater than the value B, we say that transistor is in saturation mode, and acts like closed switch in the circuit. In this mode, maximum current flows between the collector and emitter terminals. We'll make separate videos, covering in details, every mode of operation of the transistors. The values A, B, and beta are predetermined by the design of the transistor, and are not the same for every type of transistor. In next video we will go into details about modes of operation of the transistors. We will see how NPN transistor acts as a switch in circuits. Please, before you leave, show your appreciation by liking this video, sharing it, leaving a comment, and consider subscribing. Thank you, and see you next time. Bye.